The next one went up 67. That gives us an average of 58. So what we'd expect is during the past 4,000 years, our carbon dioxide should have gone up 58 parts per million. That's what it should have done. So if we add that in, do my mathematics, 58 added to 260 gives us 318 parts per million. We should be right around 318 parts per million in the ice cores. That's where we should be. Maybe as low as 300, but somewhere around 318. Now, of very importance here. You can see I have a red flag right there. Great importance. I want you to remember this. Back at the peak of the last interglacial period, 119,000 years ago, the Greenland ice core samples were 60 parts per million higher than the Antarctic ones. 63 parts per million more. They were reading 350 parts per million. IPCC says we've never been above 40 parts per million. Well, Antarctic says we were. Also of importance is back 7,000 years ago, when the Antarctic was saying 260 parts per million, at the same time, the Greenland ice core samples were 71 parts higher. Greenland was 331 parts per million back 7,000 years ago. And the IPCC won't mention it. So now we're going to reconstruct what's happened again during the last 7,000 years. We already know that the temperatures peaked 7,000 years ago, but carbon dioxide doesn't peak for 5, 6, 7,000 years after that. So what we're going to do is we have 318 parts per million that we determined we should be. The Greenland ice core samples run an average of 71 parts per million higher. 318 plus 71 means we should be at 391 parts per million. That's where we're supposed to be in this cycle that we're in. 391 parts per million. Right now the instruments are saying we're at 400 parts per million. Just made it. Wavering between 395 to 400. Well, 395 is 4 parts per million higher than what I said it was. Remember, I said that man-made carbon dioxide is only 7 parts per million. That's all that's been added to the atmosphere. So this is one proof that we're supposed to be up around 391 parts per million now. That's one proof. So the IPCC would say, okay, well, that's only one thing. That doesn't mean anything. Let's look at another item. We're going to look at one more. First of all, do we get large swings in carbon dioxide? The IPCC says no, except for man-made. This is a graphic, computer graphic, by NOAA, the federal government. On the left is the upper atmosphere of the Earth at the end of the winter of 2009. You can see it's all red. 6 months later, you can see it's changed color. What happened in only 6 months, carbon dioxide dropped 15 parts per million. In only 6 months. And now you're going to say, oh, wait a minute, why? Why? This is the end of winter. Well, you haven't had any photosynthesis all winter. You don't have plants taking carbon dioxide out of the atmosphere. So all during the winter, it's built up in the atmosphere. Built up 15 parts per million. Then by the end of summer, you've had photosynthesis, taking carbon dioxide out of the air, so you dropped 15 parts per million. That's a big swing in only 6 months. If you can drop 15 parts per million in 6 months, what do you think you can do in 100 years? So let's take a look at photosynthesis. A leaf takes in carbon dioxide, sunlight, water, gives out glucose and oxygen. In the leaflet, you have what we call stomata cells. It's like our lungs. They have lungs also, called stomata cells. If you have a lot of stomata cells, that means there's less carbon dioxide in the air, because it doesn't need as many lungs really to take in the carbon dioxide. If you have fewer stomata cells, then you have more carbon dioxide in the air. So it's a kind of inverse. So what they can do is take fossils of leaflets, analyze carbon dating, analyze how many stomata cells are in the leaflet, and that will give you how much carbon dioxide was in the air that year. It's not a mean over 1,000 years or anything like that. It's within 1 or 2 years. And this is what they come up with. First of all, on the bottom, that's the global warming cycle that I show every 230 years, okay? Remember, every 230, that's now, that's back in the 1700s. Back, this is 890 AD. That's our global warming cycles every 230 years. Up at top, the carbon dioxide plotted from the stomata cells. What we want to do is, black lines don't show up very well. Here's back in 900 AD, we had a global warming cycle. Stomata cells at the same time said carbon dioxide in the air was 400 parts per million. Wow, the IPCC they said we've never been above 300 parts per million. Well, that's 400 parts per million. Then during the course of 75 years, when we fell out of the global warming cycle and cooled off, carbon dioxide fell all the way down to 250 parts per million. A huge swing in just 75 years. But remember, the atmosphere does a huge swing in just 6 months. Next global warming cycle went from 250 parts per million up to about 325 parts per million. Then you had another global warming cycle where carbon dioxide went up, another one, another one. Now the most recent one, right here in 1850, I'd be kind of right in here where we were cold back in 1850. Instruments said carbon dioxide was 260 parts per million. That was instruments. Stomata cells said it was 260 parts per million. Ice core samples in Greenland said it was 260 parts per million. They all agreed. Then we went into the global warming cycle, and now we're up around 375 to 400 parts per million. Plant stomata say we're up that high. Instruments say we're up that high, and also the Greenland ice core samples. So this is the second item that proves that we have been above 400 parts per million frequently, unlike the IPCC that says we've never been above there. Now, we're going to get into the section that you came here for. What causes climate change, and what's going to happen in the next 100 years? This is proven Milankovitch cycles. We have the Earth revolving around the Sun. About every 116,000 years, the Earth swings out further away from the Sun. When that happens, we're in a glacial period. Less solar radiation, colder temperatures, we're in a glacial period. Then we swing in close to the Sun. That's the warm interglacial period. We went into that 15,000 years ago. And we're now coming off it. It peaked 7,000 years ago. We're actually into the cooling trend now, heading towards an ice age in another 40,000 years. So that's proven science. Now, what I also throw in here is the moon, the Earth, moon, sun, gravitational cycles. This is called the lunar solar precession. If it was not for the gravitational effects of the moon and sun, the Earth would spin out of control. Earth wouldn't have its seasonal tilts. We'd just spin out of control. So, knowing that, I've brought into play the gravitational cycles. Based on 9 years, 72 years, and 230 years cycles. And this is what happens. I showed you the Earth revolving around the sun. Well, the moon does the same thing. Here's the Earth. The moon does the same thing around the Earth. And let me just slide back to one briefly. And what happens is, on certain cycles, 9 years, 72 years, 230 years, the moon will slide in closer to the Earth. When it's closer to the Earth, the gravitational pull can rise by about 24%. That's a huge amount. And then when the Earth, Moon, Sun become in alignment during these cycles, you get another 24%. So you're running about a 46% above normal gravitational tug on the Earth during certain cycles. That's a huge tug. And you see that right along the coast. You can have coastal flooding without a storm. Lots of times in January when you have your astronomical full moon. That's without a storm. That's due to the gravitational pull. So what happens is you have this very strong cycle up 28 degrees above the Earth's equator, and there's a gravitational envelope. 2 years later, you'll be down along the equator, and then 2 years later, it'll be in the southern hemisphere. It takes 4 years for it to go from the northern hemisphere to the southern hemisphere in the very strong cycles that I use. 4 years. It takes 9 years for it to go from the northern hemisphere to the southern hemisphere and back to the northern hemisphere. A 9-year cycle is very strong gravitational cycles. That's like the full moon, and actually the gravity can be just as strong on the new moon on the left. So you have a new moon and the full moon, it's like putting a wrench on a pipe, just wrenching the pipe, and you know what happens. This is what the cycle actually looks like. The 9-year cycle, where that strong lunar gravitational cycle will come up high in the sky, right here. This is an actual cycle in 1990. 9 years later, it goes to the southern hemisphere. 9 years later, it's back into the northern hemisphere, high in the sky. 9 years later, in 2008, high in the sky. Actual cycles. These are plotted cycles for my data. Now, if you remember, I showed you the temperatures of the United States since year 1880 to now. And you can see the temperatures plotted up and below where we smoothed them out. But if you look at the little peaks, you see about every 9 years, you get a little peak in temperature. Kind of a pulse. 9-year pulse. Gee, you think that lines up with my gravitational pulses? This is why I call it Earth's natural climate pulse. Well, let's take a look. Let's look at the ocean currents. Here is the South Atlantic, the equator. This is what we call the Atlantic conveyor belt, the very warm ocean water. Comes up and just clips the southern part of the Gulf of Mexico, comes around Key West area and up the East Coast, the Gulf Stream, and heads east on out to sea, over to Europe. Here's England right here. You can see the main part of the conveyor belt continues. But one branch of it kind of breaks off and heads northward. There's England. This is the Ural Straits right here. Greenland, Norway, etc. This is the Ural Straits. Once in a while we get a warm pulse coming up in there. Let's take a look at this, the Ural Straits.